So today I'm out at the San Onofre nuclear generating station. It's actually being decommissioned and has been in the act of being decommissioned for the past 9 years. And I'm standing actually out in front of the dry fuel storage. And we're going to take a look at this and inside of the fuel pool and check out this facility and actually see how radioactive some of these things are. So let's get going.
So this is one of our whole body contamination monitors. This is called a model IPM8M. And basically what this does is we use this at the site to monitor radioactive contamination for all of our workers that go into the radiologically controlled area. Everyone has to pass through one of these successfully. This does a whole body scan to detect the presence of contamination if there is contamination. And so basically, I'll step in and show you, it'll do a whole body scan on both sides. It'll do a 15-second scan, then I'll rotate and it'll do another 15-second scan on the back side. And then if I pass, it'll give me a doorbell chime, ding dong, and then I'm free to go. If not, then all of these guys at the control point, or radiation protection technicians, would come in and they would do a frisk of me with a Geiger Mueller detector. Doug here is one of our RP technicians, and they would be looking for contamination. Okay, and then if they didn't find anything, I would get checked again. I would have to pass twice successively to be able to be released from the area. Or maybe if I was contaminated, they may have to recover contamination from my clothing or from my skin via soap and warm water. Decon methods would be deployed. So I'll go ahead and try this just to show you how. There's a couple of things here. There's a couple of paddles on the end in here that you have to depress. Also, you need to break a couple of beams. Here's one beam and there's one down by your feet. But you have to break that beam in order to activate the counter. So you can see up there that there's a yellow light on for telling me that it's checking me. And so hopefully here in a few seconds it'll give me a chime to tell me to turn around, like that one. So I'm going to do the same thing. I'm going to press in, not all the way, but in. And then these green strips here, I'm going to apply some pressure with my fingers, okay? And you have to apply pretty good pressure. You'd think they would have gave you a simple button to push, but they didn't. They gave these strips, and so you're kind of straining and hoping that the 15-second count will hurry. Yeah. Yeah. And I'm clean. Ding dong, I'm clean. All right. So now you're up.
Okay. Can I go from that?
Yeah. Now before you get in, I have to wait for the green light. So it's green now, so it's ready for you. So it does a reset. So step in, push the bars, and just right. Exactly. So that should do a count. All right. Step out, and you'll rotate and press firmly on those green strips.
Oh, that is awkward, yeah. Oh, what'd I do?
Maybe
okay.
push down on the strips a little firmer, maybe further down on the strip. There you go. There we go. Hold your breath, don't move. Most people, they do one of these and then they break the beam and then all of a sudden it stops.
Hey, trying to get comfortable, right? Yeah. Hey.
Hey,
that's nice. Looks like, yeah, you're good.
This thing is susceptible because
you
of
think
the
I should touch it?
I don't want you to go shirtless.
I have a shirt on.
Okay. I would recommend you do that because what will happen is that it'll create static, and that's radon will attach itself to you for sure.
Oh yeah. Okay.
Well, with your vest, and actually it responds the same way as your vest would. Any kind of polyester blend or polyester material, for sure. Yeah.
All right, so let's go in.
No tobacco products. You guys are smokers.
There you go. You can turn around.
Go ahead and turn around and press down those green strips firmly, and further down on that strip, the better.
It's like the beginning of The Running Man. When
I know.
Drop them into the sled.
Yeah, I know. Drop down into a tunnel.
You'll see it in your next lifetime.
All right, thanks. All right. Check and see if our equipment is hot.
Proximity detector, and that's to make sure this thing is turned on and actually working. This is just an access control feature that we use here just to make sure that people are going to be monitored while they're in the radiologically controlled area. So if you guys want to do the same thing, put your electronic dosimeter next to this. This should release the turnstile and allow you to come in. All right, so the next thing we're going to do, I'm going to reach across.
Yeah.
Normally we don't allow people to do that, but I'm taking some executive privilege We're going to use one of these monitors. This is, like I said, a small articles monitor. And we're going to use this to do a baseline check on all of your equipment. Let's make sure this passes. And it did, so that was clean. That's a good sign. The next step will be to put your cameras in one at a time.
All right.
All right, excellent. And we're in the final count. Clean, all clean. Okay. You guys ready?
Yeah.
All right, you got your PPE ready to go?
Yeah.
All right. Go down to the fuel handling building.
Yes.
Just left the rad waste control point. That's our RP, radiation protection access control point that basically is the boundary, the entry point for the whole radiologically controlled area for the power block here. Right now we're in the rad waste building. A lot of plants call it an aux building, auxiliary building. This is where a lot of pumps and isolation systems and so forth, all kinds of volume control systems for chemical injection and stuff. Filtration, all that stuff is housed in this area here. We're going to head over to the fuel handling building. All right. You don't have to be close for here anymore, Dave.
Nah, it's just like being home.
All right. So this is the outside of the spent fuel building. This is the Unit 3 side spent fuel building, and we had some security controls that were in place here that still left over. We'll go through the door and go into the building. What you'll see when we go in on your right-hand side is a large pool area, the spent fuel pool, where we used to store all of our spent fuel, which is actually now stored over on the SC pad.
Quite a door.
Yeah. This is a sign we have. Post all areas. So this is the area at the when we were briefing at the control point. The supervisor up there was talking about a yellow area or yellow pipe. That's the pipe right there. This is just normal plant shielding that we have. It's a lead shield and it's just coated in heavy plastic. There's no contamination. It's just for radiation dose level control. This was actually a cooling pipe that would supply cooling to the plant or to the pool. And so this was just an elbow where, you know, when the valve was closed or whatever, we just create like a little crud trap. So rad levels would increase, radiation levels would increase. And so we put this shielding in place, part of our normal plant processes for controlling worker exposure, just to knock down the dose rates, just so as people walked into the door or worked in this general area, it would reduce their exposure overall. So this is what we use here at the power plant. This is common for all of the power plants in the nuclear industry. This is a Heberlein RO2. It's an ion chamber design. It's a little bit different than your rad-eye. Your rad-eye uses a different detector. It uses a Geiger detector, and this is an ion chamber detector. And
So which is better?
we use these. They're both good. We use these in the industry only because the detector design is the most akin to absorbed dose biologically. All right, so this is what we always use for dose rate, establishing dose rates, so that we can, you know, we monitor and we set up all of our dosimetry programs based on what we get really from this type of instrument. So for this one, right inside the door here, and I've done all my preliminary operational checks. You can see I can put my glasses on, and I could tell you that I think what we'll see here is like 0.2 millirem per hour.
Yeah.
I don't know if you're familiar with the scale. The scale, we have basically a times 1, it says 5, 50, 500. It's basically times 1, times 10, times 100, obviously. So we have times 1 would be 1 millirem per hour. We're down on the first line there, which would be 0.2 millirem per hour. And if we went over this area that we're shielding, minor increase in dose rates up to 0.6 millirem per hour. Maybe 0.8 there. So if I took the shielding off, I'm not sure what it would be.
I'm curious, like what my my rad eye will pick up.
Check it out.
Everything I've seen here so far, I could find stronger stuff in an antique wall.
Yeah. Yeah, especially all of those, all that Fiesta ware. It's got a lot of densely concentrated uranium. And so, it's we have tours out here frequently. I used to run the radiation protection booth where we'd have all the stuff, like we had an old piece of Fiesta ware, we had a smoke detector, and we had an old, not a radium dial watch like you'd pull out of an old World War II airplane or something like that, but an older clock that still had some minor radium in it. And you know, you can take a Frisker, which has the same detector as what you have in your rad eye, and you put it on there, you can definitely see some activity. And so it's a good demonstration for, you know, radioactive components that were out there in normal living space. Let me fix the sign real quick. This is where we stored all the fuel. Usually you see, like on The Simpsons, you'll see something green glowing and something falling all over the floor and goo going everywhere. It's really totally not what happens in a nuclear plant.
It's all solid. Yeah, because it's like solid ceramic pellets.
Exactly.
Like in a zirconium, right? Is that what it is? Or
it's zircaloy, some special metal, zircaloy pins that are basically hollow, and you feed fuel pellets in. They're spring loaded so that they compress, and then there's a whole collection of made fuel assemblies, or just a collection of those pins, a large collection of pins in a specific square size, so that they fit down in those slots. And we had several hundred in there stored just from the life of the plant. And so over on our independent spent fuel storage installation, we call it ISFAC, we unloaded all those fuel assemblies into individual canisters, which had a bunch of design shielding and like its own rack inside, and loaded it up with fuel. Took it out after we cleaned it, decontaminated it, shielded it, vacuumed all the water out through a vacuum drying process, fill it with helium gas for continual internal cooling and drying, and then shipped it over to the pad where it's stored in the modules over there that we'll see later. Right after it came out of the core and was being transferred in here, and especially if the lights were dimmer, you would see a blue glow all around each fuel assembly, and that's Cherenkov radiation. That's, you know, a lot of high energy betas and stuff coming off of the fuel assembly, being refracted through elements in the water, isotopes, and basically it creates the blue glow that you see. That blue glow, which is I guess akin to this a little bit, is all you see as far as a color element associated with radiation. That's the only place you would see it, would be around a freshly recovered fuel assembly that was recovered from the core right after a cycle of operation.
So this is the spent fuel pool, where the spent nuclear fuel would have sat and cooled down over a course of about 3 to 5 years. It's very cool. Unfortunately, there's no fuel in here today because all of it has been moved to where they're doing the dry casts, of where they're storing the fuel on site. And so it no longer needs to be in this pool any longer. So this is very cool.
So while we're in here too, we're also fitted with personal dosimeters here to check our radiation level while we're inside of the fuel pool storage area. It's a very interesting place to be for sure.
There was our upender pit, and what it's called an upender pit for is because down at the bottom of the pit there's actually an upender. Basically there's a tube at the bottom of the pit that connects to the refueling cavity over in containment next door. So whenever they would do a refueling, they would remove the reactor head after they flooded, as they flooded up the cavity with pool water similar to this, and then all of the fuel, one stick at a time, one control assembly at a time, would be removed from the reactor cavity, put in an upender over there, which is basically just a hydraulically operated cell. Put the assembly in, and then it gets down-ended, and then it goes through a conveyor type mechanism over to this side, and then it would be upended where it can be grappled with this machine. This is the spent fuel handling machine. Be grappled with a tool, and then removed from the upender. It would travel through this weir gate. Of course, everything would be flooded. It's empty now, but it would be flooded just like this pool is. And it would go to a designated location in one of these racks, designated location in a rack here in the pool, and then we would keep inventory on what fuel assembly from what cycle of the outage went into what location, so that we would have a record of that.
Wow.
And so right now it's drained down as part of our process. The cavity is flooded over there, but once they're done with all of the cut-up activities, then they'll be removing that water as well, and then all of this will be part of the decommissioning process.
Now, that crane right there, essentially that's what it is, right? Since we're where do they operate that from?
Right on the bridge there, that little white box, if we were to look on the other side, you'd see a console. There's like a little chair that's there. Basically, the bridge operator would sit there, and he would operate the hoist hook up there from that console to lower, raise, to drive the bridge down this way, to trolley that way, and back and forth, so that, you know, we have a coordinate system. So the coordinate where they're going to move a certain fuel assembly that they pulled out of the core during a refuel outage might be J72 or something. I don't know. It's probably not 72, but anyways, they would use a coordinate system to go to that location and record that the fuel assembly went to that location. And that's it.
But is he manually driving it to J72, or is that like they just type it in and it goes there, kind of like a...
No, he manually drives there.
That would be a high-stress job right there, no?
Yeah. We usually, we have in the industry a contractor group that specializes in operating the fuel handling systems at all the different power plants.
Wow.
We usually contract to them. Those guys, they go from power plant to power plant all year long, and there's a team of them. They rotate in and out and go around, and they're fuel handlers. Colin, you can see from here the control panel.
There it is, yeah. How long does that exactly last?
So usually our refueling outages are cycles of many months long. And I'll tell you this too, someone might actually ask the question, yeah, but if this pool was loaded with fuel, what would the radiation levels be there? And I can tell you, I've worked here since January of 1990. I spent a lot of my life in this building and the adjacent one, and the rad levels are very similar now to what they were when this thing was loaded up. And the reason is because you have a fantastic layer of shielding right here. By design, it not only does the water keep the fuel cool as when it was stored here, but it also provides a fantastic layer of shielding.
Why is water such a fantastic shield?
Well, it absorbs neutrons, it absorbs gamma, it deflects, it's a good attenuator, plus there's such a level here. So basically the top of the racks are roughly 33-foot elevation. We have about 27 or so feet of water, so there's a lot of shielding there. There's some thumb rule equations that we use for half value, 10th value layer. In other words, how much shielding it would take to reduce a radiation level down to half of its original value or a tenth of its original value. Normally that, when it comes to water, that's a few feet. So we're talking 27 feet from the top of the rack to the top of the water. So there's a lot of shielding here to knock those high rad levels down from the fuel assemblies.
All the clothing that they change out of, that's just like, that's what they actually consider really low level radioactive waste.
Well, not waste necessarily. There's if the protective clothing reaches a certain level of contamination on usually the laundry company that we contract with will monitor all the clothes that we send them that have been used. If it hits a certain contamination level, they'll throw that away. If not, then they'll launder it and resurvey it, and if the protective clothing is at a low level, clean level if you will, then they'll send that back for reuse. The type of clothing that we use is a cloth material that has Tyvek impregnated in it, which is like a rubberized material. So it's by nature of the fabric, it does breathe, but with the rubberizing agent, it also gives it more resistance to contamination penetrating, basically particulate matter.
Yeah.
So, but yeah, it could be that a worker is putting on something that has some very low levels of fixed contamination on them. That's again why we monitor them when they come out of the area, just to make sure they didn't get contaminated. It could be that they got contaminated from the protective clothing, although it's usually unlikely. Anytime that we send stuff out, like I said, it's monitored before it's sent back, and then as part of our process, we'll do a contamination survey on everything that comes back to make sure there's no loose contamination, so there's no transference.
As we left the fuel pool containment building, we had to check our hands and feet to see if we picked up any additional contamination.
So the rule here is a ½ inch away from the surface, no more than 2 inches per second. But if we need to get a dose rate on something and we just can't reach, like maybe we're going to pull something out of the pool that we were just in, and but we can't really reach out there, but we want to check it as it comes out of the water because it may be hot, and if it comes out of the water before we get a good dose rate on it, it may, increase the area radiation levels. So we want to be able to check that thing before it gets close to us. So we use this because it telescopes way out, so we can check dose rates maybe way up in the overhead or someplace far away.
So you know what kind of like detector is on the end of there?
GM probe.
GM probe?
Yeah. 0.00, 0.01.
Yeah.
But yeah.
So what is this?
All right, so this is a TLD. Everyone on site has one of these. Every nuclear worker in our nuclear infrastructure for the whole country is issued one of these, and this is our method of determining permanent record of dose. And so basically this thing measures gammas and also has a window here for betas. These can also be used for neutron as well if need be. But this is a device that simply measures radiation exposure. Every nuclear worker has to have one of these. It's required per regulation. You're supposed to wear it on your chest along with that electronic dosimeter we were talking about earlier. And basically these things get sent off once a quarter. They get read at a lab, and that becomes their cumulative dose record. We record all of the readings for every worker that's on site that's being monitored, and that record is updated every quarter. So we have an annual total. That annual total goes against a regulatory limit, which is 5,000 millirem. All the utilities usually use 1,000. They're conservative of cumulative exposure, and it's a rare thing that anyone in the nuclear industry crosses 1,000. There are some examples, but most.
What happens to someone if they cross that?
Well, it's just more of an administrative thing. There's not like a biological problem there.
Yeah, I was just wondering, do they just kind of sit out until they deem them to be back down to?
Usually what we do is we'll give someone an extension. If they got 1,000, if they got close to 1,000, we'd give them an extension up to maybe 2,000 or 1,500 millirem, depending on the site. Basically, like I said, the government allowance is 5,000 milliroom, so there's a lot of buffer. It's just most plants administratively, they want to control it to a very manageable low level and try to, spread the dose out. It goes along with the LAR concept. I shouldn't get all the dose. It should be, actually distributed amongst, several people, so that, as one guy isn't, taking in all the risk, if you will.
He's not taking it all for the team.
Right.
Yeah, team's working for him too. The fuel is sitting 6 feet down below this level, right?
Through a lot of shielding, yeah. So we have a very hot canister, dose rate wise, temperature wise too, as you can see from all the fumes. The lid's 35,000 pounds. It's steel and concrete and rebar. And this really is just a convective heat styled exhaust port. And so there's a tortuous path that any kind of heat would have to come up through to exit the module itself. And so the shielding is pretty robust. The canister itself that the fuel is sitting in is very robust, provides a lot of shielding through concrete and steel. And the dose rates are really low. As you saw, our dose rate over here was negligible, less than 0.2, and it's barely more than that here, right on contact with the module itself. And all the modules are essentially the same dose rate. Doses are pretty low. Be curious to see what you get with your instrument.
So now how tall are these, like when they're out, when the canisters are out?
I think their canister is 17 feet tall, or 18?
17, yeah,
something like that. You're talking about a structure that is a structure within a structure with a basket that contains fuel assemblies, and so there's a lot of material that goes into the construction of the storage canister itself. So a lot of built-in shielding for radiation to have to pass through before it even gets to the structure of the VVM here and the lid and so forth. So there's a lot of shielding that goes into the construction of these things, and it's all about protecting the health and safety of the public, health and safety of the workers from a radiological perspective. Keep those doses down, keep that LAR principle in play.
And what's LARA?
LARA is an acronym that stands for as low as reasonably achievable. And it's all about managing occupational exposure using time, distance shielding to manage everyone's exposure to the lowest level possible. And that's really, this is quintessential to that concept.
So now what would happen if there was a tsunami and water came over this?
Well, I think the first thought would be that, okay, all that cold seawater would probably cool everything down. Ideally, this thing is designed to have all air passages free, so that air is free to go in, and that convective heat discharge process would work.
The postulated tsunami is, I think, 27 feet, and we're sitting at 32 feet right here. So, yeah.
Okay. Yeah. That sounds like it's all covered then.
Well, it's designed, with the maximum safety factors, in mind, really.
So now there was a thing that the LA Times wrote about, where they were saying that this was going to be the new Chernobyl and blah 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 and all this other stuff. And they were talking about, I think, when one of the canisters were being moved in here, they got hung up on something, and they were saying that if that would have fallen, and the very unrealistic hypothetical of it cracking open would have actually done anything. It's like they were saying that would have evacuated the whole coastline of California doing that. And it's like, that would have been a local problem. It would have been contained to this pad and to clean up. Yeah. It wouldn't have been something to where it's like all of a sudden it explodes.
Right.
It's like, that's what they made it seem like. They made it sound like if that were to happen, it would like blow up and it'd be like a little mini Chernobyl, and it would blow material all over the place. And it's like, that's not how it works. That's not how that operates.
Yeah, we have procedures and processes in place that are specifically designed and written to guide us in addressing a situation like that. In reality, the canisters are built so strongly, welded lids and everything, that it's very unlikely that it would have split apart. If it would have, we would have had things in place though to mitigate a release. I think that at worst it would have been a local issue where we would have controlled the release of rad material. We would have entered our E-plan, we would have made notifications, we would have put actions in place right away to deal with the event. As far as dose to the public, primary method we'd use would be limiting access. No one would be allowed in here except for mitigation teams, which would probably be, mostly our own on-site people. And then the second thing that we'd be concerned about would be any sort of an off-site release of particular or primarily gas from the release of the can, if it would even broke open.
So it's usually like xenon gas or
something like that, or some sort of a krypton gas, would be probably the big one. But regardless of that, there's a dilution factor that would, be in play. Wind direction, there's a lot of things that would, have to be, just right for that worst case scenario to happen. And fortunately, we're bordered on one side by the ocean, so there'd be limited concern there. We have on the other side, we're on the Marine Corps base, so there's not a big population zone. It would have to be something where the wind was blowing directly north, and but I don't think that would have even been a problem, because it would all been something that we would have been dealing with locally with our own mitigation efforts.
I was just curious on what your take was, about it, because I already had my opinion about it, and because it all seemed very far-fetched in what they were trying to sell people.
Yeah, I think if you saw the design of the can, it's unlikely. It's super unlikely. I mean,
it's 5/8 inch 316L stainless steel, and I mean, the little coupon I have that's the size of my hand weighs 3.5 pounds. I mean, it's just in these weigh 50 tons loaded, and Holtec did an analysis after that and found that even if it had could have fallen from 25 feet and not breached. So, obviously you would have had to, deal with any damage to the fuel assemblies inside. But yeah, it would have been a very hyper-local event. We have 3 emergency action levels currently. We had 82 when we were operating, and we're down to 3 now, and none of them involve radiological material leaving the site. So, that's why we don't have sirens anymore throughout the community. We don't have a 10-mile emergency planning zone. We don't have any of those things because they just can't happen. So,
okay,
the level of safety has gone way up.
Yeah. So now I wanted to walk around and check out the radiation levels myself using my rad eye. The levels I found were extremely low, especially considering how radioactive the fuel assemblies are 6 feet below me. I did see the readings shoot past 500 counts per minute, but that is also extremely low. This is the highest reading I got while checking out the dry fuel storage in this area.
Now this dry fuel actually produces a decent amount of heat coming out of here. It's around 120 degrees Fahrenheit, the air coming out of here. So it feels pretty warm when you put your hand up in here when the air comes and is pushed out. But it's not the air that's radioactive that's coming out of here. The air is completely uncontaminated. It's actually, the radiation I'm picking up on is from the fuel in the dry storage down here. And so I'm getting around like 350 counts per minute. I've seen it go as high as 400, and still that is extremely low. And that's pretty reassuring that this storage system can actually keep this radiation under control like this. Because I find stuff way hotter than this, not at a nuclear facility. All right, so this is the other dry fuel storage that's out here. These are from units 1, 2, and 3, but it's of an older design of dry fuel storage. And so these are really cool. They're like super big. I mean, you can't tell. This is giant.
And yeah, they are a little radioactive right here, like down here by these vents right here. And I'll show you that reading here in just a second.
Now, this may sound like a high level of radiation based off of the clicks coming off the Geiger counter, but this is about 100 times above background radiation that's being detected out of this vent. But now, let's get a little perspective, like we have before. This again is the Adams house in Malibu, California, and here on this tile, I'm getting a level that is 17 times above what I was seeing at that San Onofre fuel storage.
Like I keep saying, you know, throughout this video, I can find stuff at antique shops that are more radioactive than the stuff I'm finding here. Granted, a lot of the radiation that's coming out of this is gamma radiation, which is more penetrating, but I'm not getting anything out of this area. I'm only getting it down by the vent. And so that makes it kind of interesting, like how the radiation exposure works at a place like this and right next to old fuel in dry storage.
I hope you enjoyed this video about San Onofre Nuclear Generating Station and the decommissioning process that's going on there. This is a very interesting video to make, as this was a subject that I've always wanted to know more about. And to actually see this firsthand was quite an experience. So if you enjoyed this video, like it, subscribe, and I'll see you in the next one.